Hello everyone, this is David Berthune, and I'm going to talk about my final project for MIT Computer Graphics called Mirrored Duality, rendering a planet with a custom-built ray tracer and real-world geospatial data. So what is the motivation for this project? Well, this goes way back. There used to be a painting in the town library where I grew up that showed an aerial view of the town. The layout of this town in the painting was true to life. I recognized where many of the buildings were. However, the colors and other smaller features were starkly different. I decided I wanted to replicate this kind of artwork for this project. So there isn't too much to speak to about the background for this project because this project is fairly unique. Rendering geospatial data is nothing new. This has certainly been done many times, but usually it's done for modeling purposes or for data visualization. Here, instead, I'm rendering an artistic interpretation of this geospatial data onto a miniature planet. So what is geospatial data exactly? Well, you can think of it as any data that's tied to specific locations on the Earth. For example, a street network or satellite imagery. These are examples of geospatial data. For reference, I used a book called The Ray Tracer Challenge, a test-driven guide to your first 3D renderer. On the geospatial modeling side, I am a geospatial and remote sensing data scientist, so I'm used to working with geospatial data. Now, there are three major components of this project. The first one, which was a lot of work, was to gather, process, and organize geospatial data for all of Massachusetts, so I could build a planet for any location in the state. This amounted to over a terabyte of data. This part is a bit outside the scope of the class, so I won't speak about it too much here. The second part was to build a ray tracer from scratch using Python and Numba. I chose Python because as a data scientist, I use Python a lot, and I wanted to see if it would be possible to build a performant ray tracer in this language. Finally, the last part, and probably the most challenging, was to create the actual miniature planet from this real-world geometry. Numba was an important tool to help speed up execution of my ray tracer, and this was used in the critical parts of the code, such as geometry intersections and lighting. I was also able to implement a multi-core ray tracer with near linear speedup, using all 8 cores on my mobile workstation, for example, sped up rendering by almost a factor of 8. Performance was critical because the planet you see here contains over 10 million triangles and over 1,000 light sources. One of the most challenging parts of implementing my ray tracer was developing an acceleration structure. I was able to take advantage of the specific geometries of this planet. There are no geometries inside the planet, and similarly, there are no geometries outside of the highest points of the planet, other than the asteroids. Using this fact, I was able to build a custom acceleration structure based on arteries that greatly sped up rendering. I also aggressively perform backface culling during rendering and completely ignore the backside of the planet. Other features that were implemented besides the basics, like reflections and shadows, are Monte Carlo lighting to create nice soft shadows on the planet, dynamic procedural textures, and fast point lights. I created a structure that allows me to include thousands of local point light sources with little performance cost. Here is a close-up of the dark side of the planet showing hundreds of streetlights being rendered. To build the geometry for the planet, I take the geospatial data, tessellate it into a height map, and then wrap that around a hemisphere. I then mirror this hemisphere to create the dark side of the planet, carefully stitching the geometries of these two hemispheres together. At every location in my area of interest, I know what land type it is. I know if it's open water or road, for example. I create different materials for each of these land types. For example, water is reflective, blue, and shiny. I use the other geospatial data layers to create the geometry that are attached to the planet. I create closed and connected extruded building polygons with correct normals. I create streetlights by sampling points along each side of every road. I create an asteroid field in the middle of the planet to hide some of the symmetries that are there. And I create procedural trees and shrubs based on the land types. Finally, we're going to end the presentation by showing 2 more renderings of planets. This first one is in the middle of Springfield, Massachusetts, and this next one is in Great Barrington. That's it. I know we've covered a lot here pretty quickly, but I hope you enjoyed this presentation. I'd be happy to create a custom rendering for any location in Massachusetts if you're interested. So please feel free to reach out.